Hi everyone, this is going to be a quick video about damped oscillations. So we'll consider spring plus mass systems, except we'll add a damping term. This figure over here shows an example of situations where there can be a damping term, and that damping term will be proportional to the velocity. So the damping force is proportional to the velocity of the block. And in order to write that in a symbolic form, we can just say Fd, which is the damping force, is equal to negative b, where b is a constant, times the velocity of the block. Okay, but remember, velocity of the block, v, is nothing but one time derivative of the position of the block. So this is equal to negative b dx dt. And then we should put in a vector direction, so let's just put in x hat. Okay, so remember, the equation of motion without damping was just equal to ma equals negative kx, but with damping we now have an additional term, ma equals negative kx negative bv, but that bv can also be written as negative b dx dt. Alright, so our full differential equation, just a reminder, a is equal to d2x dt2. So using that, our full differential equation looks like m d2x dt2 plus b dx dt plus kx equals 0. Right? So this is for damped SHM, generally damped SHM. This is what the equation of motion looks like. And here, this additional b dx dt term is what's called the damping term. Great. So we gotta find a solution for this damped differential equation. We'll rewrite this equation in a slightly different manner. We'll write it as d2x dt2 plus b over m dx dt plus k over m x equals 0. And then remember this k over m, which was our omega in the undamped situation, right? So we will call that omega 0. And particularly this is omega 0 squared. So position as a function of time takes the form x of t is equal to a0 e to the negative b over 2m times t multiplied by cosine of omega t plus delta. Okay, what is omega? Omega is equal to omega naught times square root 1 minus b over 2m omega naught squared. And omega naught, as usual, as before, is equal to square root k over m. Okay, so here this a naught is the original amplitude, and as time goes on, you see that there is this exponential term. So the total amplitude, which is this that full quantity a naught times e to the minus b over 2mt, is going to slowly go down with time, and that's what you're seeing in this particular picture. The x is oscillating, but the amplitude of x is going down every time with every full period of oscillation. Okay, so this is an example of what is called an underdamped oscillation. So underdamped oscillation happens when the quantity within this square root over here is greater than 0. So for underdamped oscillations, we need b over 2m omega naught to be less than 1, or b over 2m has to be less than omega naught, which is equal to square root k over m. Alright, so that's the condition for underdamped oscillations. The system can be overdamped. So overdamping would mean that there's no more oscillations. So this is a picture for overdamped oscillation. So of course this is no longer an oscillation, it's just the position just starts at a maximum value, and as time goes on it keeps decreasing. There is no oscillation for the position. Okay, so the condition for overdamping is b over 2m omega naught has to be greater than 1, or B over 2m has to be greater than omega naught. Great. So these are two different conditions, and there is one more condition. There's this critically damped situation. So again, for critical damping, there is no oscillations. This is the orange curve here shows critically damped situation. There's no oscillation, and you can guess that the third condition is just 2m, b over 2m omega naught is equal to 1, or b over 2m is equal to omega naught. So these are the three conditions for damped oscillations. There is the underdamped oscillation, there's overdamping, and critically damped.